式的达沃斯进行。除了胡欢以外，大家都有这个。Hello, everyone, ladies and gentlemen. Welcome to ICANX Youth Talks. Every Tuesday, we have the global young scientists to get shining on this stage. So it's my great pleasure to host this session. I'm Alice Zhang from Peking University. Actually, a moderator, a founder of this ICANX, platform for a long time. So I mean, maybe most of you have met me many times. So today is my great pleasure, to host this young scientist session for the scanning probe based on the nanoscience and the nanotechnology. So today we're so proud to have three young scientists from different parts of China. Hu Huan was from Zhejiang University, and Fei Hui was from Zhengzhou University, and Xiaorui Zheng was from Westlake University. We have our panelist Xiang was from Zhejiang University too. So today's topic will be focused on the scanning probe for the nanoscience and the nanotechnology. So our first speaker is also the co-organizer of today's talk. So it's Hu Huan. Dr. Hu Huan, now is Professor Hu Huan, was working in Zhejiang University and UIUC campus institute. So this was a joint institute for Zhejiang University and the University of Illinois. So actually, Hu Huan, I know Hu Huan long time, since I don't know, PhD or some time, more than 10 years. So Huan was received a BS and MS from Tsinghua University and got a PhD in IUC. So it stayed there for many years, right? So ES, and he also, a postdoc training at IBM. And then he went to this a new institution. Actually, feel proud of that. This is also a bridge for his training in China and his training in US for UIU campus in Zhejiang University. Huan was a long time focused on the advanced nanofabrication. So he published many papers. He also win a lot of awards. He has, especially, he has granted, for 19 U.S. patents and six granted Chinese patents. So he is really an inventor, good at an innovation. So Huan was received the ICANX Summit 2022 Excellent Paper Award. Based on his invention, he also started up a company. So we're proud of that, as a company already. So Huan, stage is yours to share your story, please.
Thank you so much for the kind introduction, Professor Zhang. Now let me share my screen. Okay, hello everyone. It's my great pleasure to share my research results on special scanning probes and their applications in nanoscale fabrication and measurement. So I'm from the 7th campus of Zhejiang University, called the International Campus of Zhejiang University. We're in the center of Yangtze Delta region, China, halfway between Hangzhou and Shanghai. This is not a cartoon image. This is a real photo of a beautiful campus. So within this campus, I'm at the Joint Institute of Zhejiang University and University of Illinois at Champaign. And we also have Zhejiang University and the University of Edinburgh Biomedical Institute, and also an international business. So as Professor Zhang already introduced, I focus on advanced micro nano fabrication and try to apply them in different fields. I've published 45 journals on different fields, centered on engineering, but also applied in chemistry, materials, optics, and biology. So my lab is called Nano Manufacturing and Biomimetics Lab. So I have three major research directions. So today I'm going to focus on advanced nanofabrication and nanomeasurement. Okay, so before my talk, I want to acknowledge my students, Xiaorui Zheng, and postdoc Paul Zoma. and my collaborator, Professor Xu Yang and Professor Peng Yitian, Dr. Xiaorui Zheng, and Professor Panko. Okay, so this is the outline of my talk. So first, I'll introduce this very important instrument for nanoscience and nanotechnology, atomic force microscope, and as a core component, FM probes. Then I will introduce you three unique and special FM probes and how they can be applied for either nanofabrication or nanomeasurement. And finally, I will draw a conclusion and give an outlook. So first, AFM is the sister technology of STM, so scanning tunneling microscope. So IBM Zurich scientists, they invented scanning tunnel microscope. So basically, under extreme vacuum, and if the conductive tip is close to the sample, the tunneling current has a relationship with the distance. So by maintaining the distance the same, so the current is the same, so you can raster scan the sample and get atomic precision images. So they published a paper in 1981 and won the Nobel Prize in Physics in 1986. However, the technology is limited in vacuum and also in sample category, also only conductive or semiconductor materials. So in 1986, they worked with Stanford professor and also a professor in Europe and invented atomic force microscope. So they replaced the distance and the current with the van der force with the distance. So they can maintain the distance with the same, so the force is the same. So in order to measure the force, they use a laser to shoot at the back of the micro cantilever. So use the laser spot to reflect the spot movement to get the displacement or deflection of the micro cantilever. So this technology greatly expands the application scenario of this technology for air, for liquid, and for non-conductive, even biological samples. So this is the first atomic force microscope paper published in 1986. Now it has been cited for more than 23,000 times. And you can see the growing number of publications centered on atomic force microscope and has wide applications in biology, medicine, materials, semiconductor measurement, and also tribology. So FM is originally invented as imaging tool. So it's the only tool that can achieve atomic or molecular resolution imaging in ambient conditions. So they can do all kinds of imaging. So not only morphology, but also magnetic, optics, and also electrical. You will hear the succeeding talk about conductive FM. And not only imaging, so they also found this can be an amazing tool for manipulating small objects all the way down to single atom. This one is by STM, by IBM scientists, but you can also manipulate nanoparticles, nanotubes at the desired place. Okay. So my PhD is focused on nanofabrication using FM probes. So you can imagine the FM probe provides a unique scenario where you can have a tip very close to the substrate. So this creates a local environment. So you can apply mechanical approach, or if this is within a certain humidity, there will be a droplet, meniscus formed between the tip and the substrate. You can rely on diffusion to transfer molecules to the small region, or you can use a thermal deposition. Basically, you heat up ink and do this. You can also apply electrochemical to make electrochemical reactions, optical, electrical. So in short, the tip-based nanofabrication uses scanning probe to fabricate nanostructure. So the core component of FM, which is the FM probe, similar as shown here, it consists of micro cantilever, normally made of silicon nitride, and a tip. So the tip can determine the resolution or the function, whether it's conductive or it's determining the spatial resolution. And the cantilever determines resonant frequency and the spring constant. So depending on the application, there's a variety type of probes, including conductive, magnetic, thermal, optical, colloidal aspect ratio. So today I'm going to show you three of these special probes. So first is the thermal FM probe and its application. So this is a brief history of thermal FM probes. So as I already mentioned, Dr. G. Binek invented STM and also FM. Then IBM invested this big project called Millipede. Okay, so basically, this project employs 32 by 32 thermal probes that can individually be addressed to heat up. Then you can imagine it's about 1,000 FM thermal probes can indent a polymer substrate to achieve high density storage function. But unluckily, this technology is not commercially successful. Okay, so but it has a lot of success in other fields. So my PhD advisor, Professor William P. Porkin at the University of Illinois, he applied this thermal FM probes for nanoscale printing. So this is a paper in 2006 published by Professor King. Using a thermal FM probe, you can deposit nanoscale patterns of low melting point metal or polymer. Okay, so when I became his PhD student, my first project is to expand this application of this thermal FM probe. So this is the special FM probe developed in Professor King's group. So this is a double-armed silicon cantilever with different doping. So at the tip region, it's lowly doped, so it's highly resistive, and the temperature is proportional to the resistance. So you can apply very simple feedback loop to control the temperature of the probe at a desired set point by controlling the electrical resistance. So I invented a good method of inking this polymer on this thermal FM probe. Then we can do pretty smooth nanoscale printing. So if you look at this, so this is from the back of the micro cantilever. So you just need to program the tip scanning routes. You can basically produce arbitrary shapes of nano patterns of polymer. So you can view this as an additive nano printing technique, and it works in ambient conditions. So you just put the nano pattern wherever you want, and it's easy to operate. Ideally, you just need a stage control and also a thermal probe with control circuits. You can do nano fabrication. Okay, but this one is only nano patterning of polymer, so it's not the application is limited. So the first work I have done is to choose a very proper polymer material so it can be printed and it can also serve as an etch mask for transfer the nano pattern polymer to semiconductor materials. So you can see we can make silicon oxide arbitrary shapes of nanostructures by using one step of HF wet etching of silicon oxide. If you want to make high aspect ratio structures, you can transfer that to metal, for example, as aluminum. You can etch high aspect ratio structure using deep silicon etch process. We also demonstrated this one can combine with a unique etching method pioneered by Professor Xiaorui Zheng called metal-assisted chemical etching. So basically, we pattern this polymer, that etch a little bit, then pattern the deposit gold. We can make gold nano patterns. Then the gold serve as catalyst for induced etching of silicon. So we can make a very high aspect ratio silicon nanowires with about aspect ratio of 36. So this is with very smooth side edges. More importantly, I developed a method that can combine conventional microfabrication with this TBM method for fabrication NAMS device or nano electromechanical system devices. So this is by using conventional UV lithography. So we make microscale aluminum micropads. So the AFM probe can deposit polymer nanowires connecting these micropads. So the micropads, together with the nanoscale polymer nanowires, serve together as a etch mask. Then we do one-step etching of silicon so that both the microstructure and the nanostructure are transferred to the top silicon. Then we just need to etch away the silicon oxide and release the suspended beams. So we can make arbitrary shapes and arbitrary shapes of silicon mechanical nanoresonators. So if you look at this, it's about 400 nanometer wide. So at this stage, I think mostly only EBL, FIB can fabricate these arbitrary shapes of structures and to integrate with conventional MEMS process. And for tip-based method, it's simpler and cheaper. And this is just to demonstrate those devices work well. Okay, we can see they can resonate at the desired resonance frequencies. A good feature of this TBN method is it's a closed loop nanofabrication. So if we don't turn on the current, the thermal probe just acts as a normal probe. So you can do nanoscale imaging by tapping mode. So we can find the microscale paths. Then we can use the computer to define the chip scanning paths. Then turn the heat on. Then we can deposit the nanoscale polymer patterns. And after patterning, we can immediately turn off the current. The probe becomes a normal probe again. We can use the same probe at the same place to an in situ scanning, get the image. So in this way, we can immediately check whether this deposition is good or not. Compared to electron beam lithography, you cannot do that. So this is called a closed loop nanofabrication. So based on my PhD thesis is just applied this thermal FM probe for fabrication of different structures and devices. Okay, and in addition to silicon nanostructures, we can also make it's pretty good for 2D material patterning. So we have done 2D graphene nanoribbons and make a transistor out of it. We can also deposit nano patterns of polymer on non-flat substrates. So many lithography techniques, like electron beam lithography, you need to spin coat resist. But this one, we just do additive. So we can even add on non-flat or structured surface. Okay, now let's switch the gear to a second unique special probe called nanospherical probe. It's where I invented when I came back to China and its applications. So colloidal or spherical FM has a lot of applications in chip-enhanced ramen, also in tribology, micro nanoscale tribology, and also in mechanobiology. You can see this video, many white blood cells or cancer cells, their stiffness is highly relevant with the physiological conditions. So there's a big demand for measuring cell stiffness. And this is what traditional method people implement for making spherical or colloidal FM probes. Basically, they just attach, or glue a microsphere on a cantilever. So this method has several limitations. So it's limited to micrometer scale, so you cannot get a very high spatial resolution measurement. Second, they are done in the optical microscope. It's not aligned very precisely, so you will get imbalanced portion. And because it's glued, it's not very good for liquid environment, also for some extreme environments. For example, in heated environment or corrosion environment. But spherical probe has this kind of advantages because it's easy to predict the contact area. Once you can predict the contact area, you know the force, you can get the modulus or the elastic property of the sample. And also, spherical probe is great for measuring hydrogels, measuring cells that are soft. If you're using commercial sharp tips, you penetrate and break the sample. And so there is a Professor Gan Yang from Harvard Institute of Technology. He wrote a review paper stating the great need for making this microsphere probes into nanospherical probes because of the limited resolution. So there's many attempts to make a good spherical FM probe. If you look at this existing method, they're not that ideal. So the shape is not very ideal, and the position, the sphere is not at the center. This one looks pretty good, but if you zoom it in, it's made of small nanoparticles. So I invented method using focused helium ion by accident. I found out these helium ions can implant, penetrate through the silicon crystal, single crystal silicon lattice and swell the silicon. So we can swell the silicon exactly where I want it. Let's say this is a commercial FM probe. I use FIB to cut a flat plateau microscale, let's say 1 micron. Then I can focus the helium ion beams in the center precisely, and I can control the size just by controlling implanting area. And we can use this to do topography tests, compare with a commercial FM chip. The resolution is just a little bit worse, but you can still see the graphene wrinkles pretty well. So this is the cross-sectional TM image showing the dose test we have done to optimize this spherical probe. So if at a low dose, for example, 1,000 ions per nanometer square, you get a little bit of swell, okay? But if you increase the dose, these helium ions, high energy helium ions, they gradually lose their momentum and they dwell underneath the silicon substrate and become nanobubbles. If you keep on increasing the dose, they can merge into microbubbles, and eventually they come up out above the substrate. So our dose test agreeing well with what's the report by Intel company. So they also reported at no defects and subsurface dislocations, similar like here, and a subsurface nanobubble. They also report subsurface microbubble. I think we are a little bit one step forward. We are microbubbles above surface. One very important characteristics of this swelled silicon is it's super smooth. So we measure the surface roughness using FM. So the bare silicon wafer we used is 0.13 nanometer. After swelling, the surface still has 0.28 nanometer. It's about a few atoms roughness. And in terms of roughness, for 3D spherical surface, we're 10 or 100 times better than existing other 3D nanofabrication techniques. So this is a comparison of conventional semiconductor nanofabrication. It's a thin film deposition. You can at least make some grayscale spherical surface, but you can never achieve this super smooth spherical surface. So with this one, we can take advantage of the small resolution. We can provide 150 nanometer in this case, spatial resolution, adhesion force mapping between two surfaces. And if we do a quick calculation, we can design the spring constant of the micro cantilever from 0.01 Newton per meter to 100 Newton per meter. And if we can detect the displacement in the vertical axis by 0.1 nanometer to 1 micron, using this, we can achieve a force range of 1 piconewton, about 100 micron. So this is a big range for measurement. And what's more interesting is this silicon nanosphere is super robust. It's monolistic. So we repeated cycling for about 10,000 times. There's no bad things. Okay. So we got some cover article and got some media press. And if you look at the property of this, so this is a commercial probe. After about 1 meter scanning, the commercial probe will become 380 nanometer. You have no idea where your measurement will be. But for our nanospherical probe, we apply the same normal force, scan the same distance. We only get a little bit accumulation due to tribal chemical effect. And if we repeat this on a quartz surface, it's even better because quartz surface is pretty clean. our surface morphology doesn't change at all. But for sharp silicon chip, it even melts. So our recent results shows this can be applied for improving heterostructure quality of 2D heterostructure functions. So these two Nobel laureates, they both wrote a review paper promoting 2D material heterostructures. In some sense, it's a way of atomic manufacturing for next generation electronics, opto-electronics. So it's considered a core technology for post-Moore era. So, but the real situation is when you stack 2D material together, it's very easy to get contaminants trapped between 2D materials and also air gases and bubbles. So in order to get good measurement, you have to circumvent these regions using EBL. So there's a different methods to improve the 2D material heterostructure surface, including thermal annealing, plasma treatment, chemical baths, and atomic force microscope is one way. However, if you're using conventional sharp tips, you can only work for small bubbles. Once it's become big, it's hard to remove. But for nanospherical probes, because it's hollow, it's super smooth, it doesn't damage the 2D materials. You can apply larger forces, and the size is also pretty good. Kind of comparable to those big bubbles. So we can remove all the bubbles. And if this is the 2D MOS2, this is the 2D full bilayer MOS2 materials deposited on HBN. If you don't do this treatment, there's bubbles there. If you measure thickness of this 2D material, give you 3 nanometers. But after scanning, you can get very smooth surface, remove the bubbles and contaminants away. You can precisely get 1.4 nanometer resolution thickness. And it can promote the photoluminescence property of 2D materials by more than 150 times. And recently we did a comparison. We treated the surface both with spherical probe and sharp probe. You can see the sharp probe even broke the 2D materials. The PL peak lost, but our spherical probes clearly remove the bubbles and improves the PL effect. So the last one is a high aspect ratio FM probes using ion-induced platinum deposition. So we can control the diameter, height, shape, and also we can control the tilting angle of this tip. Okay, so then we find out for measuring high aspect ratio trenches, if you're using conventional sharp tip, you cannot touch the surface, touch the bottom of the sample. If you're using no tilting tip, it's still because the FM probe cantilever is not perfectly parallel to the substrate. It's also hard to get to the bottom. But with the FM probe with a tip at the desired tilting angle, we can precisely measure the trenches. And we also demonstrate the application of this high aspect ratio probes for measuring micro nanoscale liquid droplets, for measuring the forming mechanism of rain droplets under the influence of contamination. Okay, so I have 2 minutes. I want to draw the conclusion. I hope I convinced you 3 unique FM probes. A thermal probe can be turned into a desktop nanofabrication prototyping machine. A nanospherical probe gives you smooth surface and can measure interface force very accurately. And the high aspect ratio probes can measure high aspect ratio trenches and surface tension of liquids and micronanometer. So if we look forward, can we envision the FM be a platform for nano or molecular scale device prototyping platform? If you look at the construction field, they're made of many building cranes. They just transfer the building blocks or the bricks to make a building. Well, I actually using the second speaker's beautiful diagram. Maybe you can view the FM as nanoscale crane machines. We can do manipulation, in-situ measurement, and doping, improving the contact. So maybe this can be exciting technology for the future molecular device or atomic device prototyping. So finally, I want to end with the pioneer of nanotechnology, Professor Feynman. He wrote in his lecture, "There's plenty of room at the bottom." So I'm thinking there's also plenty of room on the looking looking seemingly small but big face on the cantilever. We can integrate more functions and apply to more applications. With this, I want to thank you for your attention.
Okay, great. Juan, yeah, you really did a wonderful work. I mean, yeah, 30 minutes, you covered, many things. I think there will be a lot of questions coming later. So we got to the panel discussion for the questions. Okay. Yeah.
Okay,
So
thank you.
let me introduce the second speaker. Actually, so today I'm so proud to have our beautiful young ladies, also my townmates, from Henan, Hui Fei. The name was so beautiful, meaning you can fly, how lovely it is. So, Hui Fei was associate professor at the Zhengzhou University. She got PhD both, from two universities and joined Suzhou University and Barcelona University. So I love that city. And there is a PhD. He did a lot of work, also visit all over the world. He visit MIT and visit Cambridge. So University of Cambridge. So that's a beautiful experience. And who was also a postdoc in Israel. So meetings, where during your postdoc and education, you already travel around the world, right? Yeah. So you have published many papers and also got a lot of awards. And now she is associate professor at the Zhengzhou University at my hometown. I'm a Henan. Yeah, so proud of that. So Hui, the stage is yours, please.
Okay, thank you. Okay, thank you. Thanks a lot for the Professor Zhang's introduction. Hello, everyone. My name is Fei Hui. I'm from Zhengzhou University. I'm very happy to share my work today through this ICANX platform. The title of my presentation is Application of a C-AFM for two-dimensional materials and nanomemristors. This is the outline of my presentation. First, I will give a brief introduction about the history and status of C-AFM, and then I will introduce the development of graphene-coated conductive nanoprobes. Most people may know that conductive AFM, which is C-AFM, is an extended model of standard AFM. The main difference between them is that C-AFM has three additional components. First one is it needs conductive property, voltage sources, and a preamplifier. C-AFM allows us to acquire topographic and count maps information of one sample at the same time. So this slide shows the key breakthroughs in the development of C-AFM from its invention in 1993 to 2020. And we know that C-AFM is a versatile tool that has been applied in diverse materials ranging from the gate oxides, low dimensional materials, and it has been used to measure these materials' electrical properties, spintronics. Additionally, it can also be used as nanogates because of its nano size, and also can be used as nanolithography to modify the sample surface. And here, if you are interested in more detailed information, I recommend you to check this valuable book edited by Professor Mario Lanza. Here I listed the main content of each chapter, and if you want to know more information, just search and read it. Nanoprobes not only used in CFM, but also are highly required in many fields of science, including nanomechanics, nanophotonics, among other fields. And they allow fabrication and characterization with atomic resolutions. And here is the SEM image in Professor Hu's presentation. He already showed us. And I just want to briefly introduce this is the silicon bark of the chip, and this is the cantilever of the nanoprobe. And here, this is the tip that we normally focus on because it's the only part that to contact with the sample. And here is the schematic of one C-AFM, one nanoprobe. And we know that the length and the thickness of this cantilever determines the frequency or the spin constant of each nanoprobe. We normally, before we start one experiment, we need to consider which type of which type of nanoprobes we want to use and to get reliable or high resolution information, but we do not want to damage the sample. For CFM and nanoprobes, it has a metallic coating, which is around 20 to 50 nanometer. And the tip radius is very important because it determines the quality or the resolution of the images. However, the main problems of commercial conducting nanoprobes is that they wear out very fast after some experiments, especially when they bear the high contact force or the high current densities, which will reduce the reliability and increase the cost of research. And here, I show two SEM images. The left image shows one new tip, and the right shows one used tip. And we can see from these images that the exposed silicon bark and the melted metal vanish after some scans. As a result, the degradation of the tip will lose its conductivity, or in this case, it leads to repeated ring-like conductive structures. In order to enhance the durability of the conductive nanoprobes, we developed one deep coating method to obtain graphene-coated nanoprobes. And due to the extraordinary properties of graphene, such as its atomic thin layer, high semiconductivity, excellent mechanical strengths, the obtained graphene-coated tips are expected to possess high resolution, high conductivity, or high endurance. In order to prove that, we have designed a series of experiments to prove the performance of graphene-coated tip. And here we use standard CFM tip and the graphene-coated tip to measure the same samples, and we found that for the standard CFM tip, it loses conductivity after 13 scans. Here I want to mention that this is not normal condition because we want to check its degradation. We use much higher contact force, so it loses much faster. But for the graphene-coated tips, it didn't show obvious decay even after 92 scans. And the IV curves and the S image further confirmed that. Later, we have repeated this experiment at different locations of the samples, and the graphene nanoprobes always show higher performance. In addition, in the specific IT curves, we have found that for the standard CFM tip, at the high current density, it only lasts very short time, And for the graphene coated tip, it can last for as long as the robust diamond tip, which indicates that graphene coated tip has the higher performance, which can comparable to diamond probes. In addition to the enhanced lifetime, and the graphene coating can also give the nanoprobes with additional capabilities. For example, here we collect IV curves on a piece of N-type silicon substrate, and we have seen that there is a shift between the forward and the backward when we use the standard C-AFM nanoprobes. This shift is because this large voltage is caused by the potential because of the existence of water molecule between the tip and the samples. When we use the graphene coated tips, and we see a real resistance, and the backward and the forward and the backwards are overlapped. This statistical plot further confirms its low variability obtained by the graphene coated tip. We have patented these strategies and attracted investment from the Beijing Institute of Collaborative Innovation, which collaborated with Professor Huiling Duan from Peking Universities. And afterwards, we're also considering to develop scalable coating method. And this work I did at Cambridge Graphene Center, and we try to use this spring coater to coat one wafer of nanoprobes at one time. And we have tried to tune the parameters, and finally we got the next result. We have got the graphene oxide coated nanoprobes, and we can see the conformal coating, and it is possible that to get the perfect coating on the nanos 3D surfaces using this scalable technique. In the second section, I will briefly introduce the electrical qualities of 2D materials using C-AFM and nanoscale. C-AFM is a powerful tool in detecting the local electrical mechanical properties, and plays a valuable role in the development of nanoelectronics. It has been used to analyze the reliability of hafnium dioxide and homogeneities of 2D materials, also the piezoelectricity, as well as the hot carriers in field effect transistors. And during my postgraduate in our group, our first work is to use C-AFM to analyze the dielectric breakdown of CVD-grown hexagonal boron nitride. In this work, we have analyzed this boron nitride islands, which consists of 3 layers, and we have observed the layer by layer dielectric breakdown. And comparing with traditional hafnium oxide, we have compared their. We have seen that the hexagonal boron nitride shows more reliable information than the hafnium oxide, because it doesn't show the obvious reliability problems such as charge trap or D-trap, among others. And in addition, I also studied the electrical homogeneities of CVD-grown boron nitride. This work I have done at MIT. At MIT, I tried to learn how to grow thin layer boron nitride on different substrates. Here I show the boron nitride grown on polycrystalline platinum substrate. I have collected the topographic and the count maps at the same time, and we see that when we do a cross section line around among these greens, we see the current varies among the greens, but within the same green, it is more homogeneous. And we have fit the IV curves into the equations, and we obtained the thickness of boron nitride ranges from monolayer to 13 layers. And this has been further demonstrated at the device level. We characterize the device at the same green and different green, and we have found the devices at same green that show similar electrical behavior, and vice versa. So it's important to get the uniform thickness of two-dimensional materials for the electrical devices. And in the third sections, I will introduce the study of resistive switching of hexagonal boron nitride-based memristors. Memristor is memory devices with vertical metal insulator metal structures, and its resistance can be tuned between high resistive state to low resistivity under the external stresses, for example, the electrical or magnetic stresses. And normally we studied the resistance switching at the device level by patterning the bottom and or top electrodes, and we measured it using probe station plus semiconductor parameter analyzer. And in this case, we collect the total current under the whole electrodes, and it's not easy to get the local information. With the decrease of device size, it is more imperative that to develop nanotechnology to detect the local information at the nanoscale level. So here I show that this is the complete resistive switching cycle. We see one stat on this polarity and the reset on the other opposite polarity. But for the standard AFM, the main issue is that its current range and the voltage range is very limited, because in this case we can only see the information in this window. But in order to solve this, we can carry out the experiment in a vacuum chamber or in Earth atmosphere. But in order to see the complete resist switching cycle, we can try to connect SPA, which is semiconductor parameter analyzer, with AFM. And in this case, we can see the whole, we can not only see the informations in the large current and the voltage ranges, but also can apply the ramped voltage stress and the post voltage stresses. And here I show one example which collected by standard C-AFM model and the C-AFM plus SPA, and we can see here we can only see the current up to 5 nanoampere, but here we can get much higher and large the current and or the voltage ranges. In addition, we can also detect the conductive filament in two-dimensional materials or the switching or the active layer in the memristors. In this work, we first stress this device at the nanoscale at the device level, and then we remove the ionic liquid. And then the underlying multilayer hexagon boron nitride was exposed. Then we use the C-AFM to scan this tiny small area, and we can observe the dimensions and the distribution of the current conductive filaments. Combining with cross-section TEM, we can conclude the resistive mechanism, which is caused by the migration of boron ions or the metallic ions, which are crossed through the the defects or the green boundaries in the switching layer. This strategy is also feasible for detecting conductive filaments in different materials here. For example, we also repeated the experiment in hafnium dioxide. We have seen the changes of the conductive filaments under different status. For example, the fresh state and the after state and the reset. And we statically analyze the data set. In this case, we can conclude the distribution of the conductive filaments and its related switching mechanism. Overall, it is very meaningful to develop advanced SPM scanning probe microscope. And here I show one example of one AFM that I used 2 years before. Then this is the vacuum chamber, and this AFM can allow us to connect with SPA, get the current, large current range, and can conduct the experiment under high vacuum conditions. It can also allow us to mirror the samples at high temperature. And in moreover, I also in my previous prospective papers, we also proposed the multi-probe SPM. We believe that in this kind of advancement will be helpful for the science research. And finally, in the last part, I will introduce two of my recent work that I use a C-AFM to detect synaptic response. At the early stage scanning tunneling microscope, in this work, they use STM used as an metal substrate, metal electrode, and to detect the synaptic response in the neural or synapse. Well, in this work, there's a nano gap between the nanoprobes and the active layer, so which may induce less stable and high variability. Inspired by this work, we considering to use C-AFM because it has a controllable direct contact between the tip and the samples, and we can use this kind of structure to detect the signals at the confined contact areas, which can be less than 50 nanometer square. And here I have introduced in my previous slide, we connect the C-AFM with the SPA to extend its current and the voltage ranges, and can also apply both RVS and PVS. And here I shows the data that we collected. We use standard C-AFM to see the volatile resist switching, and it is reproducible and shows high variability. To observe the dynamic response, we can also apply the post voltage stresses. And here we tried to use different post interval time, and we see a controllable relaxation. And when the interval time is large, you can see that it can completely relax. But with the decrease of the interval time, we can see it shows the potentiation of these samples. And by tuning the amplitude and the width of the pulse, we can also get the repeated potentiation at different locations. By comparing with previous literature, this work shows represents a significant, big advance in terms of the red current and the small cell size regarding to the integration density. At such a current level, it happens the linear potentiation, which is can be used as a desired features for the application in artificial neural networks. By tuning the parameters and polarities, we can get the long-term plasticity, including the long-term potentiation and the depression. And we can also analyze its mechanism by analyzing this quantum conductance. And then next work is very brief introduce is we mainly focus on the small particles and characterization at the nanoscale. And here we are trying to characterize the copper nanoparticles, and we use a surface modifier to modify this kind of nanoparticles. We did the characterization, and then we use C-AFM to characterize it, and we have observed that in such structures, we have seen very ultra small switching voltage, which is 4 microvolt. So this is record low switching voltage, and we can see it is highly reproducible, and the variability is also very slow. And by using the atomistic simulation, we also analyzed the physical and chemical mechanism, which at the initial high resistive state is caused by the Schottky barrier at its interface, and afterwards it switch back to low and high resistance. Is because of this unstable copper and sulfur bonds. And finally, we also predicted its application in spiking neural networks. We did the device and the circle level simulations, which have got the help from one of our collaborators. The result shows that it has high accuracy, low power consumption for image classification. In conclusion, I have spent around more than 7 years to on this C-AFM topics. I think that this C-AFM technology is very, very powerful tool, and it can be used and help us to get more information. And in my work, we can use it to study the properties of the materials, can use it to analyze the switching mechanism or the behaviors at the local areas. And I hope that it will not stop to develop, and I hope it will have good future and help us in more and get more advancement. And finally, I would like to thank my former PhD supervisor, Professor Mario Lanza. He teach me a lot about I can say almost all the knowledge of the C-AFM I have learned from him. And I also want to thank the Professor Jing Kong and Professor Andrew Fari. And here I did the growth and characterization of hexagon nitride and the scalable fabrication of the 2D materials. So, and I also would like to thank my other collaborators and friends. Thank you.
Oh, very nice. So, yeah, Hui Fei, now you are flying on the ship. Oh, yeah. So everything was so interesting. Yeah. So I mean, yeah, I will ask more questions during the panel discussion. So let's
Okay.
welcome our third speaker, Our third speaker is Xiaorui. Yeah, Xiaorui Zheng was currently assistant professor at the Westlake University. Many may know that this was a very new type university in China. I think a lot of young, faculties like Xiaorui was have a good time there. So Xiaorui received, BS from Wuhan University and got a master's degree and Chinese academy of science. Go to Australia for his PhD. After that, he traveled to US. Yeah, then postdoc and UC San Diego and also New York. So it went to, get his faculty job in Westlake and during COVID-19. So it's really not, easy time for start academic career. So Xiaorui, yeah, we want to hear your stories.
Thank you. Let me make it full screen. First of all,
So
thank you
Xiaorui,
very much for
yeah. Okay, now everything
uh,
good.
okay. Yeah, thank you. First of all, I'd like to thank I Can Talk the platform, Professor Zhang to invite me, and also like to thank Professor Hu and Professor Hui to invite me to share this very interesting topic. Today, my presentation will also based on scanning probe technology, and the application side, I will introduce some demonstrations in nanoelectronics and some optoelectronics applications. Uh, I'm from School of Engineering at Westlake University. This is a new university, and I joined the university back in 2020 during the COVID, and have my own independent investigation from 20 about 3 or 4 year almost 4 years ago. My outline is quite simple. I'm gonna first introduce the scanning probe technology and also give some demonstrations. I think Professor Hu and Professor Hui has already talked a lot about AFM. In my understanding, I have shown some images here. Uh, the AFM was introduced, or scanning probe technology was introduced because people want to see smaller world. For example, we all know for a point meter in a light imaging system, the focusing capability is restricted by the point step function of point emitter, which means you will have the Rayleigh criteria to dissolve two particles. So that's why the optical imaging resolution is limited by the numerical aperture of the optical system. In order to see smaller the STM or AFM, the scanning probe-based technology, has been invented back in 1986. 1981, and has won the Nobel Prize in 1986. To my understanding, the scanning probe technology has two core parts. The first one is the interactions. So the interaction means we have a tiny tip has different interactions with the target samples. The second core part is the feedback. The feedback means we have interactions, but we need to know what type of interactions by feedback. Feedback, the system can give the user the accurate multiple interactions between the tip and the sample. So interaction between the tip and the feedback can give us a lot of informations and also capabilities to manipulate samples. So if we look at the history of AFM, uh, people gradually integrated many parameters from liquid phase measurement to dynamic and force, and also multi-parameter here. It explores various interactions, including physical, chemical, or biological, multi-parameter interactions, and for molecular imaging, multi-frequency imaging, and even incorporate an optical system for tip-enhanced optical applications. So all these are, again, back to the two parts. The first core part is multiple various interactions between the tiny tip and the sample. The second part is the feedback. We need to know what the interactions will be. So in my own research, I started scanning probe lithography technology from fabrication perspective view. So if we look at the fabrication, nanofabrication, it's also interactions between the, for example, photons and polymers, because the polymer can absorb different photons in ultraviolet, like the mercury lights or excimer lasers or DPP, LPP, the EUV system. So all these things is also interactions between the photons and the polymers. For three-dimensional fabrication, we also know the two-photon polymerization is the polymer can absorb multiple photons at the same time, which is a nonlinear effect. This is also an interaction between the photons and the moleculars or polymers. And furthermore, if we are familiar with the electron beam lithography or ion beam lithography, this is a charged beam interaction with polymers using the charged electrons or ion beams to create tiny structures on the target materials. And in terms of the scanning probe-based fabrication, from the very beginning, STM is able to manipulate atoms in the lattice. And of course, with AFM tip, we can easily think about scratching by tiny tip on the polymers. As long as the polymer has suitable mechanical properties, then we can make some scratches. And also the very famous deep pen nanolithography from Chad Murky, which allows us to like a pencil and ink, right, to print various moleculars on the surface. And I started fabrication using the thermal probe. The thermal probe is like originated from IBM Zurich. They somehow create a thermal hotspot on the tiny tip and using the heat to make thermal interactions with the thermal sensitive polymers. So that's the ideas of interactions. As Professor Hu also mentioned, the original project was called Millipedia project at IBM. It was supposed to be an industrial project targeting as the data storage, competing with the flash memory. The resolution side or reading part is pretty amazing. The really challenge is the throughput here, because each tip can create patterns, serials. You want to parallel application, we need to introduce this multi-beam array system. Here it shows 4,000 thermal cantilevers. So this can create a lot of challenges. First of all, is the individual dressing of each cantilever. The second is the considerable heat power assumption and heat generation while during the operations. So later on, in terms of the industrial application, it failed, but it later I move on to the scientific part. So I'm gonna show you one example. This is I did my postdoc in New York University under supervision of Elisa Riedo. Professor Elisa Riedo converted standard Booker AFM system, which is a multi-mode 8. As you can see here, we made our own cantilever holder. The difference is we use a PCB board to attach the cantilever. By the way, the cantilever is from Professor Hu's supervisor, William King at UIUC. So this cantilever is very special. As you can see here, it's made of silicon, but at the top of the cantilever, there's a low doped resistive region. So this region is the carrier concentration is low. and the bridges cantilever in the region, the carrier concentration is high. So if we can flow a current or apply a voltage, we could have a Joule heating accumulated at the apex of the cantilever, and this heat can transmit it into the tip, the apex, so that the tip can be heated and burn the polymers. I'll show you an animation here. Um, so as you can see, the tip is burning some polymers and creating structures, and during the retreats, the tip is measuring the contour, the topography at the same time. So this is what I mentioned, two core parts. One is the interaction. Here is the thermal interaction with the tip and the polymers. The second is the feedback. The tip is measuring the topography at the retrace. So with the interaction and the feedback, we are able to replicate precisely the three-dimensional nanostructures on the thermopolymer. As you can see here, this is a three-dimensional contour written using a tip or burning using a tip on the polymer. At the very beginning, the design and the real topography has a gap in the beginning. And later on, because we have feedback, we know the pattern is not deep enough. So we can increase the parameters of patterning in order to match this topography and the design. So this is the power of feedback. We call it the closed loop lithography. Okay, so here is the technology. When I joined Westlake in 2020, and I proposed to further explore the scanning probe enabled or scanning probe based technology for applications in nanoelectronics and nano photonics. So what type of advantages or innovations in this system? The first part is fabrication. Apparently, we can use the thermal interactions, or we can introduce also the laser interaction, the photon interactions to make nano fabrications. The real innovation here is the stitching or overlay, because the tip again can give us the feedback of the topography. So we know what we have fabricated in the same time simultaneously. Then we can do the stitching and overlay fairly easy. I'll show you an example. Second innovation in fabrication is the grayscale, because tip has a Z direction control of the height, so we could burn a three-dimensional or 2.5-dimensional grayscale pattern on polymer. In terms of the second innovation is the characterization, because tip again is a scanning probe technology allows us to do the scanning probe based microscope. For example, topography or C-AFM, just like Professor Hui introduced. And also by introducing the laser system, we are able to measure the spectrometer, including linear spectrometer and nonlinear spectrometer. And also we integrated the circuit, the electrical probe station here, or the semiconductor analyzer to measure the electrical properties that which is well beyond the capability of normal AFM. This is also introduced by Professor Hui just now. So all these things can be done at the same time, which means we introduce the interactions and we get the feedback at the same time in electrical, optical, and scanning probe-based microscope. The third innovation part is the manipulation. Manipulation here usually is based on the also the interaction, because the tip can introduce many different in manipulations, including thermal, of course, electrical, mechanical, and I would also introduce here how to use the manipulation. So again, with the fabrication, characterization, and manipulation capabilities, I would like to explore the demonstrations or applications in nanoelectronics and nanophotonics. Here, I'm gonna show you a few examples. So the first example I would based on the nano electronics. This work has been done by my in my postdoc. Uh, the field effect transistor is a very hot topic by two-dimensional materials because the ultra atomic thickness of the two-dimensional materials allows the ultra short channel of a field effect transistor so that the gate is also able to control the on and off. Uh, the construction of the field effect transistor is fairly simple. We have a source and drain and a gate oxide, gate oxide and gating electrode. The real challenge for two-dimensional field effect transistor is the contact. This is well known. So because the metal and the semiconductor has an interface, the interface has many problems like defects or whatever Fermi level thinning this shortage barrier, all this kind of thing, challenges make the contact resistance very large. So my first work using scanning probe lithography is to improve the contact resistance by modify or by control the quality of the interface between metal and two-dimensional materials. So we invented a two-layer lift-off process, which has a sacrificing layer and a thermal resist. So the tip is heated and evaporate the thermal resist. Then you could open the contact area for the metal deposition on the two-dimensional materials. So the uniqueness, first of all, is tip before patterning. The tip is able to locate the position of the two-dimensional material. This is one of the feedback to tell the user where the sample is. Then we could easily turn on the heater and do the patterning on the thermal resist because the resist is it is a sublimation process, so there will be a minimal residue from the thermal resist. The really challenging part is the sacrificing layer. We need to use chemical etching to open or to do make the undercut on the sacrificing layer before the metal deposition. So here is also at that time is also corrosive from the chemicals. But anyway, we can try to tune the mechanicals here, then to create some doped region on the two-dimensional materials. Then, because we can dope the interface between the two-dimensional materials and the metal, that's why we can greatly reduce the contact resistance between these two samples. Anyway, here is the results. Contact resistance versus sheet resistance of the materials. So basically, you have the sheet resistance representing the carrier concentration of the materials, and this is the how good the contact is. So these two lines representing the contact made by EBL, and these three sections of line represent the contact made by scanning probe lithography. As you can see, we have reduced the contact resistance at using the same materials with the similar carrier concentration. So this is a good reduction of the contact resistance. And what is our goal? Our goal is this line. This line representing the industrial requirement in order for the two-dimensional field effect transistor to be used. So we still have a room to further improve the contact resistance towards the requirement. Okay, this is the first work using tip for the fabrication. The second work is also from my postdoc. As I mentioned, the tip can make nano fabrications, make patterns. Also, the tip can do some manipulations. So here in this example, we use the tip to burn the materials or to heat the two-dimensional materials directly. So there is no polymers, no photoresist or thermal resist. We use the tip to heat up to a certain Celsius, 300 Celsius, and we heat the molybdenum disulfide flake directly. As you can see in the topography images, there will be no scratching, or we keep it minimal scratching on the TMDC flake. After scanning, we measure the Kelvin probe force microscope. This is another scanning probe based microscope, measure the Fermi level of the sample, which representing the carrier concentration in the sample. So as you can see, after the thermal scanning of the TMDC flake, the carrier concentration has been modified. Okay, so this is another way to show the manipulation of carrier concentration, which in turn is the electrical properties in the TMDC. By tuning the environment, the gas environment, we could burn the sample to N-type semiconductor or burn the sample to P-type semiconductor, simply depending on the gas flow. If we can flow inert gases, we can dope the sample to N-type semiconductor. If we can change the gas to another gas, which can dope the sample to P-type. So here, it's easy to manipulate the channel to a diode, convert a channel to a diode, converting consisting P half P channel and half N, and we have achieved 10 to the power 4 rectification ratio on a monolayer TMDC. This is good results in my postdoc. Okay, the next example I'm gonna show you is my first round of PhD student. We're using, again, scanning probe lithography to fabricate transistors, field effect transistors, but we choose a very difficult sample, which is a TE, tellurine. That is an bipolar materials in order to fully explore the bipolarity, which is the N-type conduction and the P-type conduction. Together, we need to control the interface of the transistor. So here, as I mentioned in my previous work, this sacrificing layer has to be etched by corrosive chemicals. But with the help of this student, Hao Ting, he developed another sacrificing layer that can be etched by IPA and water, control the ratio of IPA and water. This is less corrosive than before. Then we can preserve the interface of this sensitive PE materials and observe the bipolarity of the field effect transistor. As you can see, the P-type conduction and the N-type conduction, they all achieve very large on-off ratios. And why we can get this bipolarity is because the interface. If we go back to the same images I showed before, is the contact resistance versus the carrier concentration in the materials, we have further improved this dependence towards the quantum limit, which means if we recall the first work I did in my postdoc, this work has further improved the contact resistance. Okay, and based on this work, because this is bipolarity, we could introduce dual gates to control the P-type and the N-type at the same channel, and we can form the, of course, PN diode. And but in order to do more, we converted this PN dual gates configuration into a logic operations, which can perform 7 basic logic operations within just one single field effect transistors. Okay, so this is one example. I think I'm approaching the end of my talk, but I'll show you a few examples. The second example is another first round student. We make a memristor here, the metal insulator and the metal. So in the insulator, we use the tip to create artificial defects to allow the conduction filament to form at precisely at the defects. So we can improve the reliability of a memristor. For example, this IV curve dependence is random because without defects, the filament can create it at random places. After patterning, we can artificial create the conducting channels, then we can greatly reduce the span of the set voltage or improve the reliability. and also we simulate some like LF, leaking integrity, and phi simulations. And we also use our real memristor in this circuit to mimic the heating responses from the memristors. Okay, the third example, really running out of time. This is another example. Using tip to control the oxygen vacancies and also like control the filaments. So the advantage or innovation in this work is we have a further interface between the second half, top and bottom. Here we can have the not only memoristic behaviors but also the rectifying behavior, so that this can greatly reduce the snake current between from the adjacent cells when this cell is in working, and the adjacent cell may have snake current if this is not rectifying. But we have in our in our cross point memristor array, the snake current is as low as 0.1 picoamp. This is quite low as the background. Okay, a next example from the first round student is manipulation using the tip to introduce nano indentation of two-dimensional materials. This nano indentation can make the symmetric lattice to asymmetric. Then we can create ferroelectric transition of the materials, which means if the materials in the beginning the materials is non-ferroelectric, after the nano indentation, we measure PFM in the same time we get the ferroelectric signals. This is one example. And also it helps us to understand in micro scale, the strain-induced second harmonic generation is also a sign of ferroelectricity. Okay, and this student working on another project, another collaboration with Ai Xuedong and Liu Kaihui, Professor Liu Kaihui and Ding Feng in Beijing. They synthesize ABC stacking boron nitride, and we use the tip to somehow switch the polarization, the ferroelectric domain of the HBN, and this is the pattern we wrote in using scanning probe microscope. And also, I'm gonna skip a few slides, but this is a PFM characterization to prove this domain switching are real. And also, we observe the STM evidence. After switching, we have the ABC stacking switched to ACB stacking. This is fairly critical results to prove the switching is real. Okay, I don't think I have time for the nanophotonics, but I'm gonna show you two quick examples. This is scanning probe lithography fabrication on TMDC flakes. The challenge part here is to create asymmetric structures, nanostructures on the TMDC materials. So this is the critical part for the applications in self-hybridized BIC. The second part is the grayscale. We can fabricate grayscale structure on the polymer to explore multiple resonances on the optical surface. Okay, I think I'm approaching to the end of my presentation. To do a quick summary, so at Westlake, we are working on scanning probe enabled technology, mainly on fabrication, characterization, and manipulation for the field of nanoelectronics and nanophotonics. And here I show you a lot of collaborations because this is a tool-based technology. So we have a lot of collaborations in terms of these three parts of innovations. Finally, I'd like to thank my group member, especially PhD students. They work fairly hard, and I also always challenge them for extra innovations in their project. So I really feel grateful for their good efforts. And also, I'd like to thank our collaborators. They all help us for a lot of projects. So thank you very much. Welcome to. I'd like to take any questions. Thank you.
Okay, Xiaorui, yeah, great. The time control is very good. That's the last minute. Yeah. So we're so proud to get 3 young scientists. It was so exciting talk. I mean, especially Xiaorui, though you are, I mean, she'll be very young, on this stage and got the position was during COVID-19, but since done so many interesting works already. So yeah, let me before go to the panel discussion, let me introduce our panelists. Actually, today we are so lucky to have 3 young scientists outstanding, and we have our excellent, panelists, the senior one. Yeah. So Young, yes, welcome you, Young P. Use talk support of the young scientists. Professor Xu Yang from Zhejiang University. Actually, he's a very senior one, the famous one. Was graduated BS and from Tsinghua University and then I use for PhD. And back to Zhejiang University. Now it's done many interesting work and experience works in it's microelectronics or nanoelectronics. So we are, in the same field and proud of Young's, achievement in last, 10 years. Really amazing. So today you got your colleagues, and collaborators and here. So yeah, welcome to join us and for the questions. And let's everyone move to this panel discussions. I think we start from Yang, please. Professor Xu Yang, yeah. Question, please.
Yeah, thank you. Thanks, Professor Zhang, for your nice introduction. And actually, it's my great honor to be here and discuss with our junior and young scholars. So I learned quite a lot about this nano AFM-based fabrication, synthesis, and some characterizations. So they have a lot of interesting work going on recently, and I realized this is a great research directions, especially for our emerging nanotechnology and nanoelectronics, also nanophotonics. So according to Professor Zhang's schedule, we're going to have some questions to our young, excellent research scholars. So maybe I can start one by one. Is that okay? All right, and so maybe I will ask Professor Hu Huan first. I think Professor Hu Huan did a very wonderful work, especially for the AFM, right? So he customer designed the spherical AFM tips, and I agree. I appreciate his efforts to the nanospherical AFM tips, and he mentioned that there's plenty of room on this AFM cantilevers. I think this is a lot of room indeed. So my question is, since you can customer and redesign the classical tips, right? And make this probe with a super smooth surface. And this might be very interesting and exciting opportunity to study the topology and the heterostructures, and there's many things we can explore. So my question is, since the current tip-based methods are not very fast, right? When you're scanning on the tip, so they might have some. How about the throughput? Like, how can we improve the yield of the throughput in terms of the nano tips?
I see. Thank you for the great question. Yeah, the throughput is always a kind of limitation for scanning probe based nanofabrication or manipulation. So for a single tip, the throughput is limited by how fast you can you can move the tip, basically determined by the piezoelectric state. Of course, based on the interaction, some interaction might take some time. For example, if it is thermal FM, you have to let the heat transfer to the substrate. That will take some time. So this is for single probe. So there have been approaches for improving the throughput. by scaling up, just like the IBM millipede. You can make a big array, let's say 1,000 or 10,000 chips. But individually address those chips is difficult. So maybe in the future, if you can employ optics, for example, laser, and also some kind of MEMS mirrors, so you can individually use optics to address each chip, then let the chip to interact with the substrate. So that may be able to scale up to 1 million chips or 10 million chips at the same time. So that might be able to improve the throughput.
Yeah, that'll be very exciting, especially when we go to the real application, right? I also find you had a startup company for for selling the customer design. That's very good tips. So I have hopefully you again get a lot of attention from our users and customers.
Yeah, thank you for that. I'm actually willing to deliver those tips to our research community for free, for you to use, for other people to use, to try.
Great.
I hope to get more applications out of this very good program.
All right, good. So I also like to have some couple of questions to Professor Fei Hui from the Zhengzhou University. I think your talk is also very unique, because I realize you use the coated AFM tips to study the two-dimensional based material and the devices. And you not only study the dielectric breakdown of Hager bornitride, and you also study this kind of emerging conductive filaments of the memristor devices, as well as the synaptic behavior of our 2D Hager structures. So I think this is a very hot topic, especially a lot of people, pushing our devices from traditional Moore's devices to post-Moore, right? Post-Moore electronics devices. So here I do have a couple of questions, and because I have strong interest on your research topic. You mentioned you have the graphene coated AFM tips, right? So to study the 2D Hager structures. So now, and the contact area of this small tip is typically around 50 nanometer squares. So this is a very small area. So my question is, by using this kind of small graphene coated tips, so what is the advantage using these low-dimensional coated tips and comparing with our traditional, maybe like even compare with Professor Hu Huan's nanosphere approach? So is any advantages and disadvantages, especially when we try to study the low-dimensional devices?
Okay, thank you. Thanks a lot, Professor Xu, for his questions. That's my first work that I started, which is to develop a graphene coated tip. And at the beginning, we are considering because for the C-AFM nanoprobes, it has a very thin metallic coating, and it is very easy to damage it. Once it damages, it will lose its conductivity, and the tip. Normally, we say the tip is dying. So we are considering to take the advantage of two-dimensional materials. For example, the graphene. The graphene is very, very thin, and the graphene coating cannot increase the tip radius much, so it can keep the high resolution of the tip. And in addition, the graphene has the good conductivity and thermal conductivity, and as well as the strong mechanical strength. If we use the graphene coated tip, the graphene coated tip can bear the higher contact force because of its good mechanical strength, as well as the other issue that caused the damage of C-AFM tip is the high current density. because of the high semiconductivity and the electrical conductivity of the graphene, that can help to the nanoprobes to keep the good conductivity, and it also can disperse the heat that just caused at the small contact area. It will help to disperse the heat at this tiny contact area. So in that case, it allows us to use this graphene coated tip to make it live longer time. So this is the big advantages of this. For the disadvantages compared to commercial is that we still need to increase focus on its reproducibility, because the yield of the graphene coated tip is still not low, and so we need to develop the scalable methodology to get the graphene coated tip for the commercialization. Yeah.
All right. Yep. Thanks. I think this is a very, I would say this is very important research area, especially when we go into like nanometer, even sub-nanometer scale devices, right? So people are not exactly know what happens. Is when you go to like in situ study of these interfaces. And I also find out when you present your work, you emphasized the like low-dimensional devices, right? Low-dimensional, especially two-dimensional memristor and synaptic behaviors. So if we can in situ observe or find out the filaments, the forming and migration, the behaviors, that will be give us a lot of insights or inspiration to analyze or understand how these nanoelectronic devices might behave, right? Even how they form and this mechanism. This is very useful insight for our devices.
Yes, exactly.
Yeah. So hopefully you will give us more, excitation or even surprising, for our research future.
I hope so. Thank you.
All right, let's move on to our new scientist and Professor Zheng Xiaorui, right, and from Westlake. I'm very impressed by your new paper in Nature. So this is very exciting. And I also learned, because when I was a PhD student, I just know how to use the AFM to just characterize the surface or devices. And I also learned from Professor Xiaorui, not only you can they characterize, but also you manipulate and they fabricate, right? You can have additive fabrication and deductive fabrication of electronic devices and the photonic devices. So I think this is one of the contribution to the scientific community, initiated by our Professor Zheng Xiaorui, right? So this is very exciting opportunities. Now, I find out that you're using the cold tip and a hot tip, right? So this is, and then you can do this similar to our lithography, right? And just like our microelectronics school, usually we're using the lithography technology, patterning of devices that form the active area and source string and the gate areas. But now you can using your the lithography instead of using traditional way, but using your AFM tip, right, to fabricate this kind of contact area and improve the contact resistance. And you can also study the two-dimensional ferroelectronics. So this is very exciting research areas. So now my question is, since you can using your tip, right, to study the contact area, and you can also using this kind of we said is a lithography, right? So how about the resolution of this kind of SPL technology? Because when we go to our traditional transistors, we care about like technical note. So when we have like 22 nanometer, then we can go to FinFET, and then you can go to 5 nanometer, 2 nanometer, and now people are talking about can we go even smaller, right? Even smaller scales. So I just wonder, is there any possibility, to using this kind of your technology or your method to push the limit to our ultra small devices? So we just want to see your opinion about it.
Thank you, Professor Xu, for the first of all for the comments. Second, regarding the lithography, to my understanding, scanning probe lithography is a kind of lithography. Lithography has two parts. One is you make patterns on polymers, which is you have nanostructures, and you do the pattern transfer from the polymer into your target sample, like silicon or PMDC. So why scanning probe lithography has the advantage is in the patterning process, as you mentioned, the resolution is related to the tip size. Normally, the tip can be fairly small. Let's say, for example, less than 50 nanometer in the apex, and the resolution in the polymer can replicate the shape of the tip, which means if you hit the tip fairly hot, then you burn the polymer, then the polymer have a dip from the tip, and you get the shape of the tip. So the resolution is limited by a few factors. First of all, is how small is the tip. The second is the heat distribution. Third is the thickness of the polymer. So in our lab, we can create 50 nanometer, less than 50 nanometer structure on a thin polymer, and we can also improve the resolution by reducing the thickness of the polymer. But the question is, for lithography, we need to transfer the pattern into the target. So even we can make fairly small structure on the thin polymer, it's almost impossible to transfer the structure into the targets. So that's the real challenge. Back to your question, in terms of the transistor, the smallest we could make is, let's say, around 50 nanometer channel. That's something we could make. Anything smaller is really a challenge in pattern transfer. I think this is the answer. Thank you.
Okay, thanks. I think now maybe Professor Zhang also have some comments on our young scientists. So maybe
Yes,
will
yeah. Thank you, Young. Actually, you're excellent, analyst. Yeah, such professional, insight questions. Actually, I really learned a lot from young scientists. I mean, yeah, maybe the question go to follow up with your work. I mean, especially when you have you say that with defect, not tip, right? That was a defect on the So my question is, when you for like a micro fabrication, nano fabrication, don't want to have a defect because the defect is uncontrollable. So if you want to use that, how can you control that? So you tell us your.
Thank you, Professor Zhang. Yeah, the defects are generally unwanted. We introduce defects on purpose. We introduce all kinds of defects into the channel to guide the materials, including, for example, the N-type or P-type doping. by increasing the sulfur vacancies or introduce alien atoms into the atomic lattice. So that's kind of defects, but we can make it the quantity and the location to make it N-type or P-type doping. The second type of defect is the artificial, for example, the filaments or the conductor channel to make the insulator weak at the defect. So when you apply voltage, only the current can be connected in the weak part. So that's also a on-purpose defect. Thanks.
So yeah, I mean maybe defect is not a right word, to use for you factor, because you are in purpose design this. Yeah, so it's controllable. So I mean, yeah, I didn't come to a good word for that. I mean, I suggest that as a maybe not use defect. So big defect always come to kind of question. Misunderstanding. I think maybe and this. Yeah, but really
Thank you for the
beautiful work.
suggestion.
Yeah, really beautiful work. I mean,
Thank you.
fabrication is not that easy. Yeah. So my second question is to Hui Fei. Yeah, so buy on the cheap. Yeah, it's really beautiful work, and like Yang says that this where study of the nanoscience. In the actually, this quite out to my mind because as I'm a Chinese, but I know in my previous experience, I'm a memory here, Zhengzhou is a very good nanotechnology fabric. So, but you something have some build up for the clean room facility or something. Yeah, exciting thing.
Oh, thank you, Professor Zhang, for the comments and the questions. Yes, for me, that the work that I presented today, most of them that I did in my previous lab, because I during my PhD and postdoc, I joined the Zhengzhou University 2022 within 2 years. So it's not a much long time. So here about the facility of Zhengzhou University, that here actually we have good equipment, because we have a lab that we have lab with in the we have a lab with diverse equipments, like we can do the we can do the AFM. Here we have a clean room. Basically, in my current group, we are focusing on the smart materials and the flexible electronics. Yes, we have the facilities regarding to the fabrication, mainly about the like 3D printing, 3D printing and screen printer and inkjet printer. This can allow me to I can say I can continue my the work that I introduced to using the spin coater to develop the scalable method for obtaining the different kinds of coating on different substrate. Apart from that, we also have the like the equipment that can allow us to do most of the electrical measurements. And here I have both the SPA. Even in the labs, I can continue to use the C-AFM to connect the SPA to do the further the program for the study on my topics. Yeah, I'm very happy that actually not the school and the department supports the young scientists a lot. I hope we can get big progress based on these platforms. Yeah.
Oh, nice to know that. Normally, from Henan, we don't have a very good facility. Now it's a good
Yeah.
stories was coming. Yeah, so I hope we can, have a more young talent like you, come back to hometown to contribute science and technology. And yeah, we're so proud of you. So yeah, Hui Fei, let's fly on outside. Good,
Thank
good.
you.
Yeah. So my last question go to Huan, Hu Huan. I know you more than 10 years, I think. Oh, yeah. So now, so nice to really running fast in Zhejiang University and UIUC campus. So also got to the kind of down the way to be entrepreneurs, right? Yeah. So you already started your company, and now you want have a free samples for us. Yeah, I think I take the words right. That free samples, right? Yeah.
Yes,
So
definitely.
congratulations for this. But while I know that the fabrication is quite challenging. Yeah. So even you fabrication method looks like very beautiful, but quite challenging mass production and also the price cost. So if you want to go to market, you want got to kind of even research labs can use that. How can you get this low cost? How can
I
you
see.
control?
Yeah, that's a very crucial question for the commercialization of this probe. Currently, we just did a prototype, so we FIB cut the tip. Definitely is not a good low cost approach. But you are familiar with MEMS, so we can use MEMS to build a plateau or build a tipless cantilever. So that can be mass producible using MEMS process. Probably each tip costs no more than 50 RMB. Then the only step I need to do is to using helium ion to implant the tip. That takes less than 30 seconds. So in terms of cost, altogether, I think we can maintain that less than 500 RMB. Compared to a common FM probe, it's like a 200 RMB. But I also want to address that actually majority of FM probes in our country is imported. There's no, I'm not aware of domestic suppliers of FM probes. I think that might be one motivation on me to make Chinese domestic FM probes. So to supply to researchers and also to customize that FM probe. Just like Professor Xu said, we can measure nanometer scale currents, like Professor Hui Fei, nanometer scale temperature, and many important physics properties for device research. Yeah.
Okay, super. Yeah, I believe you can make it because in
Thank you.
last
Thank you.
yeah 10 years more than that. I see you really really kind of now we use that word with resilience, right? So you as a person who have the dream, well, you eventually made it. I believe you have made it. So yeah, super. Yeah, actually, yeah,
Yeah,
Professor
maybe.
Xu did.
Since it's not easy to gather our three, distinguished young scholars together. So maybe they kind of have some, questions in between them, right? Because they are all of them are using AFM tips. So we want to listen to their opinions and their, some ideas about the future technologies. So maybe they can ask questions.
Yeah, definitely love to do that. But I want to check with the Professor Zhang. Are we running out of time? Do we have a time limit? It's almost 10.
Yeah, we almost, yeah, but anyway, this like Yang say that it's not easy to get all of you here. So yeah, if you have questions, challenge each other.
Okay, I have a quick question.
Collaborate
Professor
together, right? Not
Xiaorui,
just
Professor
challenge.
Xiaorui. So you mentioned you create a mechanical strain to make the material ferroelectric. So, but after removal of the chip, were the property lost? How long it can stay after the chip removes?
It will lost instantly,
Okay, so you have to
immediately.
test in situ using another late
Yeah, that's
optics method.
that's the idea of in situ measurement during
Okay,
nano indentation.
I see.
Yeah.
Okay, thank you.
Thank you.
Yeah, I see lots of opportunity between collaboration of us. I actually want to try Professor Hui Fei's method, maybe collab with you to put 2D materials on my FM probe. My postdoc hasn't done this for 2 years. He cannot put 2D materials on the FM probes. I'm so happy to see your results.
Yeah, thank you. I'm looking forward to collaborating with all of you.
Okay, super. Yeah, looks like, yeah, we already gone to next step because so all of you will be calibrate. Yeah. So yeah, congratulations. Let's move on. So I still think, yeah, it's almost time. So let me move to share my screen. Professor Young. Yeah, so can you see that my screen, everyone? Okay. So yeah, Professor Xu Yang, did you think Hu Huan answer your questions? Yeah, rightly?
Oh yeah, of course, definitely. I mean, he answered the questions very well. Yes.
Are you sure? If you're sure, I will deliver this certification to you. No, if you're
Sure.
not, if you say no, yeah, I will definitely withdraw this one.
Yeah.
Okay. Yeah, congratulations, Hu
Uh,
Huan, yeah, to your wonderful
we
talk.
also we also like to use
Great.
his
Thank you.
commercialized.
Thank you, Professor Zhang. Thank you so much for this great opportunity.
Okay, super. So, Professor Yang, did Hui Fei answer your questions right? Yeah, right?
Yes, he's an excellent researcher, especially for using the FM to study two-dimensional materials.
Okay,
Thank you.
exactly, yeah. Hui Fei, proud of you, yeah. Back to hometown contribute. Yes,
Thank you.
very nice. So I think Xiaorui, and at least you answer my questions right. Okay, yes.
Thank you.
Okay,
He is also
yeah, Professor
definitely a
Yang.
teacher. Yes, yes.
Okay, so
Very good
super,
idea.
yeah.
Mhm.
Proud of you, Xiaorui. Yeah, during COVID-19, still, hard working on all these things. Yeah, keep on moving. I think, a lot of things will be coming out next. Yeah. So yeah, that's all of you certification. So Professor Xu Yang asked me, is there anything for the panelists? Yeah, I have a certification for all of you. To have any certification for the panelists. You have on my invitation here. Go to Davos Summit for your talk. Okay. Yeah. So actually, they will be.
Your
This will be
invitation.
the yeah. This will be the first ICANX family go together. And Switzerland. The Davos, the very beautiful town. So and July 11 to 12, we will host. All the ICANX scientists there. To deliver talks. So Yang, you definitely have my invitation to deliver a talk there. Okay. Yeah. So
Wow.
actually,
Thanks.
this will, yeah, we will have, 6 major topics: innovation, science, technology, investment, management, entrepreneurship. So Hu Huan, yeah, next come to Davos, so please use entrepreneur, yeah, your company, yeah, please. Yeah, so this will be a great go together, and there will be a lot of nice things coming there. Also a big party. The say that's the keywords. It's time. Okay, it's time
Mm.
to go Davos. Yeah,
Time
it's
to
time
travel.
to go together. Yeah. So
Nice.
welcome all of you to be there. And next week on the youth talks, we will have another group. Big group is for the artificial intelligence. Now, almost everyone was talk about the artificial intelligence. So no one can make topics. welcome to follow use talks on ICANX. So next Tuesday we talk about artificial intelligence. Welcome all of you to follow up. So that's all for today.先生、女士们、亲爱的朋友们，欢迎大家来参加我们的 ICANX 达沃斯科学峰会。那今年是第1次 ICANX 会组织大家一起在瑞士的达沃斯进行线下的聚会。我们有6个主要的议题。第1个是创新 innovation， 第2个是科学 science， 第3个是 technology 我们的技术，第4个是 investment 投资，第5个是 management 管理，第6个是 entrepreneurship 创业。所以它结合起来就是 It's time 是时候了，是时候让我们去达沃斯听这些非常给我们启发的关于未来的这些报告。在达沃斯我们会有3个非常重要的论坛，一个是诺贝尔奖论坛，我们会邀请诺贝尔奖获得者来跟我们谈科学的未来，我们会邀请世界科学院的院长来跟我们谈世界科学技术发展的未来。那我们会邀请大学校长来参加我们的世界大学校长论坛，来跟我们谈关于教育的创新教育的这样的一个未来。同时呢，在达沃斯呢，我们也会邀请各行各业的这样的一个非常重要的领袖人物、领军人物来跟我们分享他们的所思所想，他们对未来的思考。那我们也会邀请非常多的各行各业的精英来跟我们分享他最精华的这样的一个思想。那当然了，达沃斯这个舞台也不只是给这些大牛们展示的舞台，也是我们来展示的这样一个舞台。所以如果你有好的故事、好的思想、好的技术、好的思考来进行分享，那也欢迎你再来线上投稿。所以我们的截止时间是4月1号，大家还有1个月的时间来准备好你的发言，希望分享给全世界的。所以欢迎你在线提供你的资料。那我们也希望你成为这个舞台上的明星。那在达沃斯呢，我们设了3个奖。第1个是针对大学生的，你是创新创业的最牛的大学生，那你来申请我们的创新奖。如果你是一个毕业10年以内，现在正在从事独立科研工作的科学家，那你来申请我们的青年科学家奖。如果你是一个创业者，你成立了你的公司还不到5年的时间，已经发展得非常好，那请你来申请我们的创业奖。所以所有的奖项申请的时间截止都是4月1号。那欢迎大家在线提供这样的一些资料，那我们也会给大家非常多的这样的机会，成为舞台上最亮的星。那是时候来我们大家一起把科学推向未来，推向世界。那这个呢是我们在达沃斯的非常重要的合作伙伴，我也希望你成为我们的合作伙伴，我们一起来推动世界的发展。那现在达沃斯论坛已经开始注册了，所以各位朋友、各位好朋友们，请你们开始尽快注册吧。我们相聚在达沃斯，我们一起 Go Summit 走向巅峰。
在持续发展的社会中，电子元器件需要应对日益复杂化的要求和越来越高的期待。技术革新浪潮汹